So at our university in Singapore, we're quite fortunate to have essentially a fully functioning water treatment plant on our campus that's available for cybersecurity research. So it's a full process. You get drinking water at the end of it, although I've never tried. And across its 5 tanks is doing things like dechlorination, ultrafiltration, reverse osmosis, et cetera, and it's fully automated. So each of the 5 stages in this tank are controlled by a programmable logic controller, a PLC, which is sensing the environment and actuating, so driving the system forward. So the question that we started to ask was, how could we be sure that these PLCs have not been modified? How can we be sure that somebody unscrupulous hasn't come along and changed the program to drive it into a state where it's overflowing or underflowing or setting on fire or what have you? So we started looking at the literature and looking at some classical approaches which had been presented at this conference before. But unfortunately, we found that we hit a bit of a dead wall here because the PLCs we were equipped with were proprietary closed and we had a very limited support from the vendors. So we looked for a bit of a third way and came across the concept of physical attestation, where instead of modifying the PLCs directly, what we do is build some model of the overall system. And then as new data is being produced, as the system's running, we take that data, we judge it against the model, and determine whether it's looking abnormal or looking normal, and whether an alert should be sent to an engineer. So this is the approach we started looking into. But of course, the big question is, how do you build such a model for a system like this? So, of course, SWOT is a cyber-physical system. The control and the physical processes are tightly intertwined, and it doesn't make much sense to look at one part without the other. And while these PLCs, they're actually relatively easy to model, you can think of them in this system as being like big nested if statements without any looping, so very, very simple structurally. The physical environment is a bit more challenging, so you need to be able to model processes such as the dynamics of water flow, how pH values evolve over time, and it's certainly beyond my expertise as a computer scientist. So what we set out to do instead was to try and apply some learning to try and help us to build this model automatically. So we took a step back and looked at the 2 situations that we want essentially this model to identify. We want it to be able to recognize when the system is operating normally, as on the left, and we want it to be able to raise an alarm when the system's behaving abnormally in some sense, as on the right. So essentially what we were aiming for was to build some kind of model, some kind of classifier that sits at this boundary and is able to give you one or the other with a decent amount of reliability. So how did we do this? Well, we proposed a 5-step process, which I'm going to go over quite quickly today. Our first 2 steps are essentially concerning the collection of raw data. And then the final steps are about extracting it in a useful form, doing some simple learning, and evaluating the classifier we get out at the end, whether it actually has some utility, whether it has some use in detecting some different kinds of attacks, as we mentioned at the beginning. So the first thing we do with this green box is randomly simulate the system to try and get some raw data about its normal behavior. So I must mention that here we're using a faithful partial simulator that concerns the water processes here. When we set out this work, we wanted to be able to play with the parameters a bit without the safety concerns and the wastage of resources. And by focusing on the water flow processes, we fixed our state in our data log to be the levels of the 5 tanks in the system. So we log it every 5 milliseconds and get a big data log of how these values evolve over time, with respect to many different initial configurations, the extreme ones and randomly selected ones in the middle. Following this, of course, we want to get some examples of raw data of the system behaving abnormally. So we didn't want to do this in an ad hoc way. We wanted to be somewhat systematic. So we turned to some inspiration from software engineering, from the software testing world, and that is mutation testing. So we're not actually doing any testing here, but rather we're using the concept of generating code mutations as a way of systematically seeding some faults with this system to help us with the learning. So just to give you some insight as to how we do this, we take the original simulated PLC codes, we make several copies, and we apply a single mutation operator to each of them. So it's quite simple, it's straightforward and first order here. An example of a kind of mutations on the slide, here we're changing a relation operator, but we do other things as well, such as mutating the logic or changing a constant, et cetera, et cetera. We then have this task of ascertaining that the mutant we get is effective in the sense that it actually gives you some abnormal data that's distinct from the normal data. So I'll mention this more in a slide or two. And finally, we built a little tool that could do this for us, SWOT Simulator, fully automatically, generating your mutants and generating your data traces, your normal and your abnormal. So just an example of a mutation. This is extracted from one of the PLC programs, so it's just a nested conditional. I won't go into the meaning of it, but if you look at the bottom, you can see that there's an assignment to some state. We assign the number 19. So a very simple mutation that we do is change that number from 19 to 14. And it's a very small change, but it has the effect of triggering a completely different set of signals to the actuators, to the motorized valves, to the pumps. And so it starts affecting the levels of the tanks quite immediately. Okay, so we collect our data, our normal data, our abnormal data. The next thing we do is extract from these logs our samples, our feature vectors that we want to pass to our learning algorithm. So because this is really we want to recognize patterns between the levels of the tanks over time. It's a time series data. We want to use a feature vector of the form like this, so pi and pi prime. And our pi here is just capturing the levels of the 5 tanks at one particular moment of time, and then your pi prime is the level of those same 5 tanks after a certain amount of time has passed, so after a fixed time interval. So this time interval is common for all of these vectors. So for the positive samples, this is quite straightforward. We just go to our data log and we extract as many as possible. For the negative samples, we do the same, but also run a check to make sure that it's distinguishable from the normal behavior. So this is one benefit of having a simulator, and obviously a drawback were we to do it on the real system. So at this point, we then apply a supervised learning algorithm. So here we used SVM. The reason we wanted to do this was because we're non-experts in this area, quite frankly, and we saw plenty of success in the past of using this to build models for time series data. And plus, we also, our group comes from a verification background. We wanted to try and learn something as simple as possible so we could do some interesting verification tasks with it. Albeit that bit didn't quite work out, but we did get a model which can take a new pair of pi and pi prime and give you, with a reasonable amount of accuracy, a judgment as to whether it's representing some normal relation between the tank levels or some abnormal one. So the final thing we did was, of course, validate the model. We wanted to check that there was some statistical evidence of the model being a physical invariant of the system. So we applied some statistical tests. We applied SPRT to sample new feature vectors from distinct initial configurations and until the stopping criteria were met and this judgment was made. Some more details are in the paper. We also looked at varying some parameters, if you will, such as what kind of classification function for SVM and how large the fixed time interval should be. So I'm not going to go into these in this talk, but rather focus on these 2 questions here. How many mutants do we need? And is the model useful? Does it have some utility for detecting code modification attacks or other kinds of attacks? So looking at the number of mutants, we generated cumulatively from 300 to 700. Of course, I should highlight here that there's actually a rather poor ratio between the number that turned out to be effective at giving you some abnormal data, as well as between that and the raw mutants. So obviously this is something that can be improved by using things such as domain knowledge or some program synthesis techniques to direct the generation of mutants more effectively. Our technique at the moment is quite naive. But once we get to between 60 and 80 in our experiments, effective mutants that is, we find that the data we have starts getting a reasonable amount of accuracy in terms of in terms of classifying your pi prime as normal or abnormal correctly. With respect to attacks, we evaluated against two different kinds. First of all, we looked at some code modification attacks coming from this motivation we had to do physical attestation. So we detected, we rather randomly generated 40 new effective mutants and used our model to try and detect them, and we detected all but 7 in this case with a high level of accuracy. So the 7 that it didn't detect, when we investigated it by hand, we found that the mutants did have some effect, but a very, very minor one. So they weren't particularly effective, and probably they didn't have such enough of a physical effect on the system to be detected. Perhaps a more interesting one, the previous one was a set of randomly generated attacks. This is a benchmark of attacks produced by some researchers using this system, the SWAT system. And we picked out the ones concerning the water flow processes, which we focused on. So in particular over here, you can see that it affects a bunch of different attack points. We have NVs, which are your motorized valves, letting water into the tanks. We have Ps, which are the pumps for pumping the water out, and the LITs, which are your level indicator transmitters, essentially your sensors at the tank level. And the attacks did a few different things, starting at the ones at the top, which are quite simple. You know, something is off, you turn it on. Something is on, you turn it off. But we also had some different kinds of attacks where we manipulated things more slowly. So starting by increasing manipulating the value of the sensor by a very small amount every second, until eventually something is triggered in the system. So we were quite happy to see that all of these were at least eventually detected. Here, the accuracy means, from the moment that the attack started, how many of the feature vectors from the logs were classified as abnormal. So it's in the 90s for the majority of them. For the 2 attacks that I have designated eventually, the reason for this is because the sensors are increasing, the sensors are being manipulated by a small amount over time, and it's not until those values get to a certain point that the system triggers an actuator, such as opening the valve or switching on a pump. And actually, once it gets to those points of when the attack has a physical effect, then the accuracy from that point on is also very high, so in the 90s. Okay, so we were encouraged by these results, but of course there are some threats to validity, some limitations I do want to highlight. So first of all, this is being focused on a single system, SWAT. So you might argue that having this time interval that you're checking your data between, this might not work so well in a system where an attack can have a more profound effect more immediately. In a system like SWAT, it takes a little while for the attack to have an effect. It takes a while to fill up the tanks and overflow it, and that sort of thing. And also the code modification attacks. So these were essentially generated randomly. We wanted to make sure that our model could pick these out, whatever they were. But a real attacker is likely to be more intelligent than sort of randomly changing constants here and there. So we want to do a more rigorous evaluation of that part of the work. Also, perhaps the data collection is too onerous to apply without a simulator at the moment, but this is something we're addressing with ongoing work, with more targeted mutations, et cetera, et cetera. And we also have to assume that the data here, the data that's being logged, is not compromised. So using this on its own is risky, of course, if somebody has control of the network. But in the SWAT lab at SUTD, there are other groups working on similar projects to monitor the health of the network. So these things should be done in tandem. So some take-home points from this talk. We proposed an approach for learning models of cyber-physical systems through the simulators semi-automatically. So we evaluated it principally on SWAT, but I don't see why it wouldn't generalize to systems with similar characteristics. And at the core of this, we were using code mutation as our way of systematically generating abnormal data traces. And the evaluation has some positive signs that we might be able to use it for physical attestation and so on. But of course, there's a lot more to be done. So in light of the time running out, I'm going to skip over the future work. Of course, we can discuss it. But I want to highlight that the facilities at our university, they're not just for us. They're available for anyone to use. So if you're interested in using our test beds, we have one for the water treatment, of course. We also have the EPIC power grid on the bottom left if you want to play with electricity. We've only had one fire so far. Please let us know. Please let me know. I can put you in touch or work together. So thank you very much.
Okay, so yeah, we have time for a few questions.
Hi, this is very nice work. I'm Alvaro Cardenas from UT Dallas, and I was wondering, in your feature detection, you have only the height of the tanks, so basically only the sensor measurements as your feature vector.
Yes.
I was wondering, why didn't you consider also the control signals as well, or is that?
Yeah, so at the moment we just use the physical properties in our model, but this is we wanted to try and keep it as simple as possible and get a result with as little information as possible. But this is something we do want to look into now.
Yeah, right, because I think no model is complete of the physical system if you only look at the sensor. You also have to take into account, like if I turn something on, you see something being on, and then you can expect that be reflected in the sensor measurements. So related to that, I think, I don't know if you have seen this in, there's this theory called system identification. I don't know if you've seen it before. This is used also to learn these models by randomly exciting the system, and then you create the models. And I actually, there's a paper in CCS 2 years ago that uses that for the same test bed that you're using.
Yeah.
Would be interesting to look. I don't know if you have seen those models, the system identification models.
I would surely like to look at that in more detail.
Okay, thanks. And I think that's it. Yeah. Well, good work.
Thank you.
Hey, Chen Zhen from Temple University. I guess this work mainly focus on extracting the invariants. So I may have missed something, but I was wondering why don't you analyze the code directly to extract the invariants?
Extract the invariants from the code.
Yeah.
So it's quite difficult. We found it was quite difficult to do so without the bigger picture of the system.
Because the code is unavailable to you, or?
No, the code is available, but the physical part and this control part are so intrinsically linked that it's difficult. It's difficult to do it from the code alone.
Okay. All right. Thanks.
Hi, I'm Mary from Department of Defense. I just had a quick question on if your simulations were virtual or if you actually had physical, like, simulation of the PLC.
Virtual or physical. So the simulator itself, it's essentially a translation of the original PLC code in ladder logic to Python, and so it's essentially a Python program that we're running with a bunch of cross-validation that was done against the real system to make sure that we tightened up the model processes of the water flow. I'm not sure what you mean otherwise by the virtual or.
If you actually used a PLC for the simulation, or if you answered that. Thank
Okay.
you.
Yeah.
Okay, so we have only 30 seconds left. So one quick question from Rob.
Sure. Over here. I have a question sort of similar to what was asked before. You have sounds like a very exquisitely accurate simulation. What is it that using a machine learning technique in the middle gets you that you don't have from just the simulator itself?
It's essentially about, we want to be able to identify attacks that we don't know about. So we want to sort of build up this picture, extract all of these patterns from the data that are not so clear to us as engineers of the system or designers of the ladder logic, in the hope that if somebody invents an attack in the future that goes against these patterns, that it would be detected. So it's really some work that's gone on in the lab has been sort of manually defining invariants based on sort of an expert understanding of the system. But what we're hoping to do here is sort of make some steps into moving to that point where we can defend against attacks we don't know about beyond those.
Okay, so with this, let's thank
Okay.
Chris and
Thank you.
again.